Great. Well, thanks. Thanks, Michael. I'm super happy to be here. Excited to be able to share this work with you. I'm going to be talking about my work building Chairables and thinking about designing technology for both accessibility and engagement. As Michael said, I'm an assistant professor in the HCII and director of my lab, which called the Axel Lab. So just to start out, to give some context to this, because I think a lot of people have different definitions for what accessibility means and what engagement might mean. So choose your own definition, but here is how I think about these things. So first, my research, like I said, is focused on accessibility. So thinking about people with diverse abilities, thinking about people with disabilities and how they interact with technologies, how technology can better support and break down barriers that either society has presented or different technologies have created for them in terms of interacting with technology. So my goal in this case is more on the kind of functional side of being able to do the things that we would like to do while interacting with technology. On the engagement side, I think of engagement as kind of the traditional experience of interacting with technology, interacting with experiences and participating in society, in the activities that we would like to participate in, and being engaged and having a positive experience in those situations. So if we want to think about, if we think about this in terms of a research question, this is probably a very common question that you might find for accessibility research. So how can we design devices and interfaces that better support people with diverse abilities? So generally my research on charitable computing has been focused around this question related to how we use technology and information technology and communication technologies to support wheelchair users for Chairables. So I'll start kind of as general as possible. When we think of smartphones and mobile devices, we think of these devices as being ubiquitous and they're providing this means of interacting and connecting with people around us. The capabilities of these devices change every day, and the things that we're able to do leveraging this functionality, continues to grow. On the side of wearable technologies, with this growing popularity of the technologies and the growing availability of these devices, the impressive capabilities that I've leveraged with mobile computing become even more convenient, to the point of where it is literally right there on your body. One area where this unprecedented access to technology has the profound potential to impact people's lives is for accessibility. So thinking about how we considering people with disabilities who may have maybe dealing with other issues that technology can alleviate some of these barriers, but the technologies themselves are far from perfect. Not everyone is using the same kinds of devices, nor are they interacting with those devices in the same ways, right? So in just this image, there's 4 images captured from one of my studies showing different hand poses of someone interacting with a touch-sensitive surface, an interactive surface. So you just have people with these different kinds of hand poses, different kinds of fist postures, interacting to perform particular gestures. All of these folks are performing the same kind of gesture. They're all performing a swipe on this surface, but you can see there's a variety in how they might do that. Furthermore, we sometimes fail to consider the other devices or other assistive devices that people might be using while interacting with these technologies, like wheelchairs. So wheelchairs in particular, we can think of them as both creating and alleviating challenges of interacting with a computing device. On the one hand, the wheelchair is a mobility device primarily, but it can also limit a person's ability to reach devices or to traverse certain terrain or fit through tight spaces when they're trying to move around. So if you think of a kind of a whole body situation versus an individual device. On the other hand, in terms of alleviating some of the challenges created, a wheelchair also has spaces to carry these devices or store these devices, being able to carry and store multiple computing devices or hide wires without actually burdening the user, as we've seen with some early innovations in wearable technologies. So what is a chairable? So I mentioned the word a few times. So when my research with Chairable explores the design of devices that leverage those affordances of wheelchairs, mostly the positive ones, to support the needs of the actual user of that wheelchair. So Chairables are devices that are designed to fit the wheelchair's form factor while maintaining its shape and considering the abilities and preferences of the user. So to give you an overview of some of the research that we do in the lab and some of the things I'm going to talk about in this talk, The research we do spans a number of different areas relating to a range of different abilities and different activities. So things from designing interactive devices for wheelchairs, so the interaction capabilities, thinking about wearables and athletics, social media access, thinking about how we can actually facilitate co-design, navigation and spatial awareness, and also a newer area of AR and VR access. In this talk, I'm going to focus mainly on my work with Chairables. So talking through our initial work in terms of thinking about how to leverage the wheelchair in design, thinking about kind of the first Chairable that we built, the Rest, which was a flexible input device for power wheelchair users, and then talking about more of the work, getting into Chairables for athletes and some of the more current work that I've been doing with Wearables and SpokeSense. And then I'll finish up with some of the current and new directions that we're taking in the lab and further research. We'll start with how we've conceptualized design, thinking about leveraging the wheelchair in design. So I like to think of this as participatory ideation and design to get to the goal. So I'll preface this with kind of the problem space of motor impairments. So thinking about motor impairments and how they can affect multiple parts of the body. So in addition to using a wheelchair because of some ambulatory ability where you might have difficulty or an impairment to the legs, they may also have difficulty or an impairment to the head, neck, arms, and hands. And so sometimes these devices or the devices that these impairments or the devices that people are using can present these challenges for users with upper body mobility impairments. And the use of the wheelchair, as I mentioned, can sometimes exacerbate these existing challenges. And I'll give you a couple of examples as we move forward. And again, we can go back to that kind of original question of how to design devices and interfaces that better support people with diverse abilities. So how do we support people using wheelchairs and these devices together? So this initial study, so in general, my research involves understanding technology and people, how the current technology is working, developing solutions if an existing solution can't be adapted or modified to meet that need, and then evaluating those solutions. In this case, the more the emphasis was on the design side of how we should approach design, how do the users actually approach this challenge, and how can we involve our target population in the process of actually coming up with these solutions. And so in this first study, our goal was to understand existing challenges with technology and mobile devices and to ideate on what ideal desirable solutions might be that address the needs that these users have in relation to that. So we started with individual design interviews with individual users in their home, along with design sessions focused on meeting their individual needs or overcoming specific challenges that they identified during our interview process. We then moved to focus groups with clinicians to gain a broader perspective on what might be useful from those initial interviews for a broader group of users. So rather than focus on an individual solution, we thought about a broad range of input and output technologies and techniques. And then we went back to the users again to do configuration and design sessions with those more generalized solutions or generalized techniques. So to give you a sense of what we found during this study, so I'll give you a story about Kyle, which is a pseudonym to protect the identity of our participants. But Kyle is someone who had a spinal cord injury at a young age. He has suffered from paralysis below the neck. He's able to move his head and his left shoulder. And he uses a head array or a set of buttons that are mounted around the headrest of his wheelchair to actually control it, drive it around, and control various functions. He was also very fortunate to have an entire smart home. His home was renovated completely to become a state-of-the-art smart home, actually on an Extreme Makeover Home Edition. He was actually fortunate to have his entire home renovated, so state-of-the-art controls for different devices in his house, environmental controls, doors. He has a really state-of-the-art rehabilitation facility with temperature controls and a pool, an elevator, all these kinds of different things. And he controls all of that, all of his smart home features using this tablet. And so one of the biggest things that we talked about, or two of the things that we talked about in the interview as his biggest challenges were the positioning of the tablet and being able to control it, and the mounting dimension. So for positioning, I give you this image here of Kyle actually using a mouth stick with a stylus attached to interact with his smartphone. In a similar way, the tablet would be actually mounted to the chair using a metal arm. And so it would position the tablet so that he could reach it with this touchscreen mouth stick, right? after they renovated his home and did all these interesting modifications and updates, the last thing they did was mount the tablet to his wheelchair. And so what the challenge was that he encountered was he now has all these controls that are accessible through this tablet, which all you have to do is attach to his chair. But the mounting point on the chair sits about 3 or 4 inches to the right of his wheelbase. And so it actually extends the dimension of the chair by about 3 to 4 inches when the doors were designed to fit the chair through and allow just enough clearance for the chair to get through and maybe to turn a little bit. So he actually can't, when the tablet is attached to that mounting arm, he actually can't fit through the doors that he opens with the tablet. So he actually has to have someone come in to remove the tablet and reattach it when he goes, like if he wants to leave his bedroom, he actually has someone to either open the door and then attach the tablet once he's outside of the room, or to remove and replace it once he's already through. And so what he wanted to be able to do, so partially just to alleviate that situation, was to have other controls that he could access on his own. So a switch control that he wanted to, because he has some residual motion that he can actually lift his left shoulder, could he use a switch or a button that was attached near his elbow to control different devices, or at least to have that kind of input, in addition to the head array. And also just the real goal for him was to have suitable mounting for his display or for his tablet so that it didn't actually change the dimensions of his chair, and he can still access all the functions and features that he had, that he'd grown to like. And so some of the things that I'll get into these terms a little bit later, but this is demonstrating 3 concepts of Chairables, of this idea of always available interfaces, which is common to wearable technologies, where you have access to this device at all times whenever you need it, but also tailoring to the specific abilities of the user, which is another common accessibility approach. So combining those two, and then adding in this idea of maintaining the silhouette or the shape of the user and their wheelchair together. So maintaining their body shape in these ways, as this kind of illustration indicates. So as I mentioned, we went from the kind of individualized interviews and design sessions where we thought about those individual solutions to working with clinicians and wheelchair users in a clinical setting to get the perspective of people who work with spinal cord injury patients on the order of magnitude of 10s to 15s to 100s of patients, and work through a lot of these issues in physical therapy and occupational therapy. And so we spent 4 days doing a series of focus groups with these clinicians and a few wheelchair users to ideate on what a solution might be for a phone dialer, a game controller. In the first case, we focused on these specific applications. And then from kind of examining the results of that, we moved into a more general space of focusing on how people can input information into a system, and then how can people interact through different kinds of innovative outputs. So we conducted these on 4 consecutive days with a series of people in and out. After we came out of those focus groups, we took those results into individual design sessions focused around the different inputs and output techniques that arose from that study. And we asked individual users to once again think about how they would configure an ideal solution for them to make their wheelchairs interactive. So if we started off by asking them to identify reachable areas on their wheelchairs using a diagram similar to this one, they could identify which areas they could physically reach to interact with some kind of input or some kind of output. We asked them to then configure the inputs and outputs that they would like in those different locations, describe the functionality that they would provide, and then rank their preferences for different input and output techniques related to their configuration. And so the result of those focus groups, interviews, and sections was this kind of rank ordered list of input and output types and the ways that they might be attached or configured on the chair. And so from the input side, wheelchair integrated and wearable inputs were the most popular. Removable interfaces, which were the most common at the time, moved to the number 3 position, and then gesture-based interfaces, which our definition for gesture-based interfaces was more in-air free gesture, so actually being able to gesture in free space, open space, rather than on a touchscreen or surface. And then on the output side, head-mounted displays, which were the most novel thing at the time. The Google Glass had just been announced and released. It was chosen for both the novelty and the potential of having a very private display that only you could see but interact with in a different way. And then add-on screens as the more traditional method, and projected interfaces fell to 3rd because there were only 3 options there. The projected interfaces presented a lot of potential but at the same time, a lot of privacy implications that people just weren't interested in dealing with. They didn't want to have their text messages displayed on a wall next to them or onto another surface that anyone else could walk by and use. And so there was the overall high-level takeaway. One of the takeaways from that study were this set of 5 principles, which I use to guide designing technologies and solutions for wheelchair users that leverage the wheelchair. And so the first one is building on this idea of always available. So availability, devices should be always on or always available at the very least. They should maintain the silhouette of the user and their wheelchair. The devices should be tailored to individual abilities. We should be considering strongly the familiarity to known devices and systems, which is another kind of usability principle. We think about learnability, whereas we carry over the positive effects of prior use of devices. But also we should understand kind of the negative implications that devices have had in the past. So for a lot of the technologies that people had used, they had negative experiences with touchscreens or negative experiences with gesture-based interfaces, which kind of limited their willingness to attempt or willingness to try new interaction techniques because of their past experiences with them. So in order to introduce these, we need to understand the relationship that people currently have with those devices. And then finally, robustness to different environments and conditions of use. So one thing I think we can all agree on is that most of us, at least pre-pandemic, do not spend all of our lives in the same room or sitting in the same chair. And so in this same context, most wheelchair users, despite using the same wheelchair for most of their mobility needs, will be traveling and traversing multiple different environments, different weather conditions, different homes, things like that. And so the biggest enemy to any electronic device right now, I think we can also agree, is water. And so if it rains and you're out in your fancy electronic wheelchair with all of your devices, they need to be able to handle that. And so what did we do with that? So we took those principles and we wanted to instantiate them in some way and really to build, what does the first Chairable look like? And so we took those kind of high priority ranked preferences for inputs and outputs and came up with the Rest, which is a Chairable for integrated control. And so some of you may recognize this chair or a chair that is similar to this. This is the captain's chair from the Starship Enterprise. I believe this one is from Voyager. I could be wrong. Someone who's a bigger Star Trek fan can please correct me. But the point is, if you've ever watched the show, one of the things that you'll notice, or that you'll notice now, is that anybody who sits in this chair automatically becomes the captain, and the power of running the Starship Enterprise and leading the show, leading the crew, is now given to them just by sitting in this chair. And so this idea of the captain in command of the ship and captain of all the functionalities being attached and being centered on this one seat is kind of what drove kind of the idea of what Chairables could be. It also happens to have integrated controls in the exact locations where wheelchair users also specified as wanting to have those, and is reconfigurable to meet the needs of the particular captain who is running the ship, which controls you want at your fingertips versus farther away from you. So I'll go back to this image of, what, to give you kind of an idea of what we're designing for, what are we trying to accommodate with this as far as disabilities and accessibility needs go. We wanted to make sure that the people who are using this device would show and may show a lot of variation in the way that they move, as well as the hand positions that they might be using to interact with this surface. And so in each of these images, if we start at the top left, you can see this person with an open palm, very loose kind of orientation of the fingers. And as I mentioned, they're all performing the same gesture, a swipe from the back of that touchpad to the front. And so for that person, they're doing it with that one finger and sliding forward with their hand staying open the whole time. On the top right, you have kind of a loosely clenched fist where they're doing it more with their knuckles. Person in the bottom right with a very tightly clenched fist where they're doing it more with kind of the bottom of that fist. And then the person in the bottom left where their hand is actually contracted due to a lack of rehabilitation. And so they're actually in a much more awkward position to try to press down on the surface using the top of their finger. But our device needs to be able to work in a similar way or in the same way for all of these folks with these different hand positions and poses. And so the Rest FSR, which is the longer name, or force sensitive resistor, is a pressure sensitive input device rather than being capacitive for touch and gesture input on the wheelchair armrest. So ideal location, integrated controls. So the idea was to enable users to perform familiar gestures, but actually using the surfaces of their wheelchair, which they're already accustomed to, rather than having to have a set of switch controls, which you would need to mount multiple, or having their smartphone device out at all times. So what this allowed us to do was to support multiple interactions in a single area, making it possible to replace 2 or more switches that would take up the same amount of space with a single input surface. Also, what this allows us to do is not to explicitly need to detect individual fingers and instead rely on the pressure being applied to the surface, which allows the users to perform the gestures with different parts of their hand or even using a different kind of tool. In addition to common touchscreen gestures that you might think of when we think of touch gestures like taps, swipes, and drags, slides, and things like that, or pinch or multi-touch, I think single touch gestures, we also came up with a set of 5 special gestures specific to the armrest because this is a form factor that we really want to leverage and get the most out of. And so we came up with these 5 special gestures, the first one being the squeeze gesture, where it's a common action you probably do with your armrest of your chair. If you have one, you might squeeze the end of the armrest, and we can use that as a deliberate input to the system to control some functionality. The second one, which is also one of my favorites, is the lift gesture, which if you've ever paid attention to the word, it's an arm rest, not an arm raised. You actually rest your arms on the surface for the majority of the time and deliberately lift your arms off as an action. So we can detect that and use that as an input to the system as well. What does this mean when you lift? The punch gesture, which is by far the favorite of participants, something that you would like to do but cannot do usually with your very expensive smartphone, is to be able to apply a direct and solid force against this armrest and actually be able to measure that force and understand that it was a punch or very swift motion. The roll gesture and the rock gesture, the roll being rolling your hand from one side of the armrest to the other, and the rock being able to do that alternating from inside and out. So we followed a similar approach to the previous study where we involved both individual wheelchair users and clinicians to gain both an individualized perspective and a broader perspective for multiple patients or multiple users. When we evaluated these, we conducted 2 evaluations, one where we specifically explored the FSR version of the GestRest, where it's a pressure-sensitive armrest-based interface. But we also wanted to understand whether just by having the inputs in the right location, whether that was enough to alleviate some of the issues. So it's always great when you come up with a new solution, and that solution is definitely the best. But also we want to understand if just placing the touch screen of the smartphone closer to your fingertips where you need it and having that be integrated would also be something that's suitable. So we wanted to really understand that. And so we tested each of these devices and asked participants to rate and describe how difficult it was to perform each of the touchscreen gestures as well as our special gestures, and then rank their preferred interfaces out of 4. So they ranked out of these 4 which ones were their favorite. Luckily for us, thankfully for us, happily for us, the FSR version of it actually did end up being the top ranked device. But in terms of ease of use, all 4 of these devices made it significantly easier for them to perform these different kinds of gestures than actually having to use their smartphone or other device. The reasons why it was suggested that this was their preferred device for both wheelchair users and clinicians, because of the flexibility that input offered them in terms of being able to interact with multiple parts of the hand or using a tool while maintaining that similarity to the touchscreen in terms of familiar gestures that they might perform. This middle image I want to draw your attention to just for a second is one of the things that our clinicians did, our occupational therapists did instinctively once we brought this device in, is to say one of the things that we commonly do in the clinic when we're working with a patient, especially someone who might have a contraction of the hand or something, we want to be able to support their hand properly. And so we'll often build up some support on top of their existing armrest using foam or clay or some other tool. And so if we are doing that and you have this interactive armrest surface, how is that going to work with our foam? And so they went and grabbed a block of foam and tried to all of the different gestures. And for demonstration purposes, they all worked. So they were able to perform the swipes, the taps, the presses, all through this dense foam. And so the density of the foam would obviously impact that, but the general idea, the flexibility to still be able to do that was maintained. So I want to kind of cycle through. So this has been kind of a discussion of interaction technologies and Chairables. So I wanted to briefly touch on what comes after the GestRest and what is kind of the ongoing work in this space. And so the big space for us right now is the interaction and smart wheelchair. So when we think of smart, I have smart in quotes, so you can think of smart being autonomous or smart being, well, connected. And so some of the things we want to do is also examine more emerging interaction techniques and how those can translate or be applied to the wheelchair, how those can be applied to chairs in general, beyond wheelchairs, but being able to facilitate more expressive interaction for people using wheelchairs. So being able to take advantage of the latest in force-based touch interfaces, proximity-based interactions, what kinds of things can we support this way through an integrated means? And I have a special interest in dual purpose sensing. So being able to use the same kinds of sensors, the same type of sensor, same interactions for both controlling interfaces interacting with the environment, but also to understand more about what the users are doing and their state, whether it be for health or wellness purposes or just for monitoring and understanding what's going on. And then I also mentioned about the AR and VR accessibility space that we're also aiming to extend into as we think about how the fine-grained motions that are now possible to perform, especially using the latest VR technologies. A lot of them rely on these hand controllers, which are able to detect the precise positions of your fingers and are allowing you to perform more fine-grained motions. And so what does that look like for someone with a motor impairment who may not be able to perform those specific motions, but still can benefit from interacting in a VR space? So for this next part of the talk, I want to shift the focus from more interactive technologies and specifically how people with motor impairments might be interacting with devices to thinking about what kinds of chairables or wearables would be good for athletes. And so this is work, I'll talk about wearables and then talk about a system called SpokeSense. So the question kind of driving this work is more, how can we design more inclusive activity monitors for people with differing abilities? So there's still a theme here, but we're thinking specifically about activity monitors given the prevalence and popularity of fitness and activity trackers at the time. So there's, we have all these companies investing hundreds of millions into this fitness tracking and fitness and activity monitoring space. But we were seeing, especially back when the study was conducted, this really low adoption of these technologies among people with disabilities. And so there were two schools of thought on this, whether it was because of the affordability of the devices, how new they were, or whether there were accessibility barriers that specifically created challenges for people who might benefit the most from these kinds of technologies. So our approach to this was we started with looking at, what wearables were out, what wearables were available on the consumer side to understand, what were features of these devices, what functionalities did they provide to different users, what was their intention, components, et cetera. We had conversations with experts about the design of wearable technologies in general and about specific devices they worked on. We conducted semi-structured interviews with athletes and coaches. I'll get into observations and talk about the National Wheelchair Basketball Tournament and how that fits into this line of work. And then development and testing of actual devices, by which I mean SpokeSense. So basically, this is the result of our early explorations into the space of wearables for fitness. Most of the devices that were available at the time were they looked or worked very similar to the Apple Watch that you see here. Most of them were wrist-worn in form factor. They had some kind of a screen or at least a light, and they had roughly the same kinds of motion sensors attached to them, so they were able to do the kind of basic motion tracking and step counting. Early on, we conducted a bunch of these studies and identified a lot of different challenges that people might have faced with wearable technology designs, especially with respect to wearables, especially as we consider the differences between different bodies, right? So the human body is really an extraordinary thing. It's extraordinarily adaptable to change. Whether these changes occur early in life or later in life, our bodies are really able to adapt to changes caused by traumatic injuries or disabilities. But these things can really change our body shapes and our physiology. So what and how we're able to adapt is really profound, thus making these different options a challenge. So the first one that we saw was just in terms of body location and sensing. So if you remember the foot pod, the little device that you might attach to your shoe, which would give you feedback on your steps and your gait, your running speed, heel strike, and all that kinds of information. I would like my encouragement of these kind of crude examples, but the first example is, what if you don't have a foot to attach the shoe to, then you can't put the foot pod on the shoe, which essentially removes that as an option for step counting and activity monitoring. You might say that the next option is physiological, where you can adapt new sensing types to understand different elements of your body and your exertion. Analyzing one promising approach would be sweat sensing. So actually analyzing the content of your sweat. Apparently when you exercise a lot, you release certain enzymes in your sweat, which can be measured and then can give you feedback on how much exertion you're experiencing. One of the interesting facts about spinal cord injury is a condition called hypohidrosis, which is the inability to sweat below your injury level. So if someone has a very high level injury, say a C5 or up here in the neck region, below that injury level, they may not have a reduced ability or even inability to sweat, which makes temperature regulation very difficult. In terms of sweat sensing, if you're wearing the wrist-worn sweat sensing device there, if you're diminished ability to sweat, we can't get a very good signal from your sweat and thus making that technique ineffective, at least in the body location presented. Despite these very kind of crude examples, the biggest barrier that we saw for wearable technology adoption was actually just misperception of the devices and misperception of what they could do. So this quote from this wheelchair rugby player, I really love to use. These devices, they track steps and I do not take steps. So if I'm supposed to take 10,000 steps a day, I don't take any steps in a day. I use my chair, I move around. The second one from a hand cyclist, mother of 3, who is also an elementary school teacher. So I can imagine this person is never sitting still, never not moving. I'm sitting, yes, but I'm constantly rolling around. I'm always interested to know not steps, but how much I'm actually moving around. I'm never immobile. This picture is not of the actual person. This is a picture of Tatiana McFadden, who is a Paralympic wheelchair racer. But you get the point. The people are moving around. They're never sitting, they're never sedentary, really. They're not really actually like sitting still. So what's revealed about this is not only that the words and perceptions of the devices are different, but in some cases, the actual activities that we're interested in monitoring can also be different, which led us to ask, what would appropriate solutions in this space do? What would they look like and how would they best be used? And so I have a couple of reasons for why we chose to go with sports. There's a number of different activities we could have gone with. We could have gone with everyday activities. We could have gone with everyday motion training. But in general, one of the big reasons why we went after sports is if you think about modern day sports, especially mainstream sports, they're all driven by metrics, whether it's digital metrics or not. They're competitive. The engagement in the physical activity is well motivated. So it's not something that we have to deal with the confounding variable of this person is active on Tuesdays and Wednesdays or Fridays. We know that if they're playing the sport, they're going to be active at least while they're playing the sport. And they're interested in numbers because that is what drives the sport. Baseball essentially is just statistics. I don't know if anybody actually plays anymore. I think they swing the bat and then they count. Similarly with all professional sports that you'll see if you dig far enough. So I decided to start with wheelchair basketball as an example wheelchair sport because of my personal connections with basketball, but also the opportunity to get engaged with the professional organization, the National Wheelchair Basketball Association, which runs one of the largest adaptive sports events in the country, bringing together about 1,000 wheelchair athletes for a weekend, which rivals March Madness in terms of content and competition. So if you think March Madness is spread out over the month of March, the National Wheelchair Basketball Tournament is all of that in a weekend. It's about 88 games on Friday, 80 more games on Saturday until you have 3 champions in the adult division, 3 champions of the junior divisions. Wheelchair basketball in general, for some background, is based on traditional basketball where people are standing up and running around, but adapted for use using a wheelchair. So some of the rules are changed and they're using specialized athletic wheelchairs. One of the other really interesting facts about wheelchair basketball is that it uses a functional classification system, which assigns each player a number or score for their functional ability to perform motions required for basketball. So someone with a very high level injury or high level severity of impairment may end up on the 1.0 side of that scale, where someone who has very limited impact to their mobility or their motions may be a 4.5. And so the way that this plays into competition is that you can't have more than 15 points on the court at any given time. So you have to have a mixture of people with different functional abilities playing on the same team in different positions. So it gives you a sense of kind of equitable competition. So what we did in this space was we worked to develop SpokeSense, and this Liam here was gracious enough to allow me to use his image and to pose holding up our device as our official spokesperson for SpokeSense at the tournament. So we conducted these kind of early studies, but over the course of 3 years, we got to explore the space of this activity tracking and solutions for wheelchair basketball. We did these early studies at the national tournament where we did, a few interviews and a large 76-person survey of athletes and coaches to ask them about their preferences and ideas, desires for devices that they might use, or desires for metrics and information that a wearable device may provide. And so as a result of those interviews and the survey, we came out with a set of the information that people were interested in, some of the metrics. So they were really interested in movement, speed, acceleration, and distance. They were interested in the number of pushes, respiration and breathing, and heart rate information. So things related to kind of stamina and fatigue management. Number of pushes is something that was available at the time via things like the Apple Watch, but it's still understanding how that movement, how the speed and acceleration actually played out was much more important to them than knowing the number of pushes. You can imagine a soft push will make you go maybe a couple of inches, and a hard push may make you go a couple of feet to yards or even all the way down the court. I think it's also important to point out, for the purposes of the work, we actually expected that what would come out of this would be another wrist-worn wearable that these players and coaches would be interested in using. But it turned out that the form factor of the device was much more important than we expected. They were very interested in something that could attach to the chair, which is good for Chairables. But the reason for it was because the devices themselves, the wrist-worn devices, wouldn't be considered permissible in competition because they would be considered jewelry. So they wouldn't be able to be allowed to wear them during the games when they really want access to that data. They could use them in practice, but not in competition. So we set out to fast forward a bit and look at actually wheelchair trackers and monitors, which there have been some developments, but the majority of the available trackers that people could use were more data loggers, which required post hoc data analysis. So you would have to download the data after the activity and then process it, analyze it in order to get any feedback. And in some cases, you'd have to wait even over months of the data and then go back and say, it's great that on Saturday, March 15th, you had this really great workout. It's probably irrelevant to you now, but now that you can see the data, we can probably do something with it for next year. So we were aiming to provide real-time feedback for them using our device. And so this is SpokeSense, which is a prototype prototype device for wheelchair basketball to give immediate feedback on motion metrics like the ones I described, specifically speed, distance, tilt, and others related to moving around, specifically in the chair. And so I'm briefly going to talk about the interface and the study we conducted at the 2018 wheelchair basketball tournament. So to give you a sense of the device, it's a very small IMU with a microcontroller, a 9-degree of freedom IMU to do orientation and motion metrics from both wheels of the chair, so one on each wheel. And we were giving the athletes feedback on things like speed, distance, peak speed, acceleration, deceleration, braking, the turn direction, and orientation of their chair. We also included a microphone on the device in order to provide some indication of environmental factors, environmental features, and I'll go into a little bit about what we did with that. But first, I want to call your attention to kind of the orientation change events. So some of the things are obvious that you might think of for orientation, understanding the orientation of the chair. Like if someone is tipped over and may have fallen out of the chair, it's important to know that, or maybe an important event of interest. And another important event what people will also do is to actually tip or tilt up onto one wheel to gain a height advantage. And this is something that actually you can train for. So not only are we detecting the kind of obvious events where you tipped all the way over, but we can also detect when you have tilted up onto one wheel and actually be able to measure and give feedback for that. So I'm going to let Patrick Anderson demonstrate this for you. So you'll see, he actually takes the wheel off of the chair while still balancing on those two wheels, pushes it around, and because he's a show off, catches it and reattaches it before coming down. So just like, what you're seeing and kind of this amusement, I will let you know my best average for being able to do this was about a minute and not continuously. So a minute over the course of a day where I maybe got up on the wheel a couple of times. But being able to track this as an elite skill, this can gain you that kind of competitive advantage. And we want to be able to give feedback on those kind of specific motions and specific activities that they might be doing. As I mentioned, we also included a microphone on the device, because you can imagine if we're recording data about all these motions and all these metrics over the period of a game, which lasts about an hour, you can imagine that's a pretty long data stream. So how do you know actually what types of things might have happened in there? How do you know where to look for something interesting? Maybe if you're not looking at the video, or if you want to have some kind of easy indicator or way to segment that data into usable segments, right? So we actually used game sounds and a project called Acoustics, which uses a small sample of recorded game sounds combined with audio collected through existing sound libraries to train a model that we use to detect the buzzer, dribbling, the basketball, and the referee's whistle. And so we use that to just kind of drop markers in the data of when something interesting might have happened, or when a person, so when somebody's dribbling and doing these other motions, how fast are they while they're dribbling versus how fast are they not? How fast, when a buzzer happens, it's either a substitution or the end of a quarter. We tested this. We had a kind of an open demonstration and a short interview, which we conducted at the 2017-2018 tournament. You can imagine that players and coaches do not actually come to tournaments to be parts of research studies. So we had to keep all of our interactions very brief. But despite that, we were able to gain a lot of really interesting data and learn a lot about kind of the benefits or potential benefits of having this device, which provides this real-time feedback. And so some of the obvious things were for goal setting, gives you having this objective data gives you something that's immediate and very concrete. So you're able to set your goals based on this kind of known performance data. But the one that I want to call your attention to, which is something that we often overlook, and it's casual comparisons between your peers or between yourself and elite athletes. So I asked you to compare yourself, or I asked myself to compare with what LeBron James is able to do on a basketball court. How high does he jump? I can get that information really easily and say that he jumps higher than me, but not for long. For these casual comparisons with these elite athletes, this data is just not really available to them, whether it's because no one's collected or just because it's harder to collect in the moment. And so being able to make these kind of casual comparisons between your elite peers was something that was really desirable and something they saw as a potential here. In addition to that, being able to evaluate your intuition. So when you're an athlete and you're competing with teams, you kind of have a sense of what another player is able to do or what another team is able to do. But can you actually compare yourself to other people in your position or other players with your same functional classification? So you have this idea. So as from this, what the quote suggests, so as for teams competing with each other, you already kind of know what to expect from intuition, but you can add some objectivity to confirm or refute those intuitions and see where you actually are versus a team or someone you have less experience playing with. And finally, one of my favorite experiences from the tournament was actually this idea of facilitating competition. And so this apparently humble stretch of concrete, once you add some cones and lines, people immediately start to just fly through this as kind of a speedway. Once we added the actual metrics on a large display and people could see when you have the sensors on, how fast you're going, it became something to be the best in the building. And so this gentleman here came back to our booth, I think about 6 or 7 times in different chairs at different times of day, just to make sure that he was the best and the fastest person in the building compared to anyone else who tried using the chair. And for a long time, he was the fastest in the building. There was one person who got faster than him and clocked in around 12.5 miles per hour in a wheelchair. So pretty extraordinary stuff and pretty fun to actually be able to be in that space. Also, in terms of augmented review, we can augment the existing practices that people have for interacting with this data. We see a lot of potential for this in terms of ongoing development that we're working on. So being able to facilitate team management, working in other sports, analysis for everyday activities, and actually using, again, the dual purpose sensing, where spoke sense right now is more for understanding how you're moving, but can we then translate that as input to a system or an interactive experience? As I mentioned, in this space, technology roles and adaptive sports is one area where we're looking to extend this work. So thinking about sensing and feedback system in other sports, so like wheelchair tennis or beat baseball, rugby, or even sled hockey. For the last few minutes, I just kind of want to tease a couple of the other projects and new directions that I'm going in, mostly in the interest of time. The first one is kind of along a thread of work. So the next, actually, I'm going to mention about 3 projects relating to social media access. So along with former PhD student Cole Gleason, we started to do this kind of social media accessibility exploration where we looked at Twitter and thinking about how social media content has really grown and become increasingly visual. And despite the prevalence of images that are available on this platform, our analysis in 2019 revealed that most of the images, 99.9% of the images on Twitter, actually had image descriptions. So the image descriptions are the descriptions, the alternative text descriptions you can provide to let someone with a vision impairment know, or a captioning program, a description of the image if they're unable to see it. And so the feature existed, but very few images actually had these descriptions. And so we were interested in exploring ways to automatically add alternative text to these images, either post hoc through another tool, or ways that we can support content writers when they're actually producing these descriptions in the tool. Twitter has since made very extraordinary leaps in terms of making that a better experience and more accessible experience. But another really fun project that we've been able to do is kind of looking at different types of content. So within that space of images on social media, we extended that work, finding these different types of images. One really prevalent type that's become really important to our society and how we communicate online is memes. We may not use these macro memes as much as we used to in the past, but most of these images are not fully described. So you may get a description of the text, you may get a vague description of the image, or you may just get the word image as an actual description, which doesn't really communicate the humor and the experience of why this image was shared in the first place. And so what we were actually interested in, what we did was we explored alternative ways of presenting this content, from first identifying the type of meme and providing, if we knew so for these types of memes, they're repeating and the text may change, but the background image doesn't. So being able to convey the text and the description, as well as to be able to convey the audio involved, or convey through audio the humor and the overall message of these. So for image C of the Velociraptor meme, we had some very celestial background music, and then it would read off the text in the same kind of screen reader voice of, if the opposite of pro is con, is the opposite of progress, Congress. And so that, just having that celestial background music to give you the feel. And recently we started exploring how access manifests in videos and video search for people with vision impairments. How do they find videos on YouTube that are accessible? How do they experience access? What makes videos more or less accessible? And how do you actually choose which videos you're going to watch? And so this is going to be presented at CHI in the coming year. Another quick teaser, just because I think we are just about out of time and I want to have time for some questions. This project is actually looking more on the navigation side, orientation and mobility, getting into how people move through space. But I think we can all agree that we've been seeing these really interesting bumpy tiles at the edge of the curbs for many, 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 many years, and they haven't really changed much. What you may not have known is that they all have actual very specific meanings that they are supposed to have, or relatively specific meanings to indicate certain types of hazards or to guide people in specific ways. And if you don't know what those meanings are, you're like most people and most of the people that we talk to through our survey of people with vision impairments and non-visual navigators. Most people don't know these meanings, to the point where even the orientation and mobility instructors advise people to not trust what you think that indicator means and use other factors. So we're interested in building and expanding the space of interactivity around these types of devices, whether it means adding multimodal feedback to interaction with these in indoor spaces, or being able to communicate with other devices around these ground surface indicators, or even be able to customize them in a more efficient way, such that they become more beneficial to the users they're supposed to benefit. And then finally, interested and started to explore this space of accessibility, mobility, and transportation relating to autonomous vehicles and access within those vehicles, as well as the impact of autonomous delivery robots and micromobility options on the curb, on accessibility of the curb. So people traversing pedestrian space now also interacting with these robots and autonomous systems. And so with that, I want to acknowledge my collaborators and funding support for this work. And thank you all for listening, and I'll take questions.
Thanks very much. We have a few questions that are already in the form. As a reminder to everyone, if you would like to ask a question, please submit it to the link I just sent out. Panelists, I'll ask a couple on behalf of the students, and then feel free to jump in with any questions you have. One we have who did a reverse image search on your captain's chair, says it's from the J.J. Abrams films. So now we know. Says he found the tipping and tilting wheelchair really amazing. Was curious how you implemented that.
So it was actually not too complex. So because we have a sensor on both of the wheels, we can tell the relative position or the relative orientation change of both of those wheels using the magnetometer and the orientation sensor that are already built into the IMU. And then we can average that and actually set just a threshold of when we know that you've tilted all the way over versus we use kind of more of a trial and error process to figure out the right orientation change, and actually ends up being relative versus a exact measurement. So at the moment, we're not measuring whether you're 15 inches off the ground or 16. We're measuring whether you are tilted and balanced versus whether you've completely tipped over and now the orientation of the wheelchair is completely changed. And so we then reset that periodically so that we know if you're moving and staying in one plane, we don't have to then like the sensors kind of move around. So we need to know whether it's relative to your current position.
Wondering, because folks' abilities are so diverse and specific, how you think about the line between creating bespoke solutions and generalizing your solutions for a larger set of abilities. So how do you balance those two?
That's a great question. One of the, at least with the Chairables work, that's one of the goals of why we went after the wheelchair as a platform rather than specifically targeting certain types of disabilities or certain types of motor impairments or limitations. Because one of the common factors there is the actual platform, the chair that they're using is going to be very similar and have similar features. So the way that I typically approach this is to find something that does provide that common ground, and what really to kind of tease out where the modifications are most necessary versus where there is more opportunity to have a generalized portion of the solution. So it's kind of, if we have a base platform that is more common, we can then start to slightly adapt at that level, and then we get much more fine-grained once it's actually with the user, and you can then personalize your custom setup. So the gestures that the specific gestures you might use with the gest rest versus the actual gest rest type.
So in that sense, does it make, when I think about the stakeholders for these kinds of designs, there's the end user, but it also seems like I'm sorry, I forgot the term you used for them, the sort of occupational therapist essentially becomes a real critical part of the design process, it seems like.
It definitely influences it. I think one of the goals that we have is to try to capture as much of that knowledge, much of that generalized knowledge of the therapists, the clinicians who are working to design solutions for multiple people. They're working with a range of folks. And so when we did our focus groups and our design work, we asked them to think as broadly as possible of the people that they're working with. So try not to kind of counterintuitively, try not to think of a specific person when you're designing the solution, and think of as many people as possible, what could be useful for them. And so you often end up with something like, well, if I can't choose for this person specifically and that person there, I'll either make the button bigger or put the button in the right place. And so that was, kind of the approach there.
Okay, thanks. Panelists, this is a good moment if you'd like to jump in.
I had a question. You presented 5 different sort of things to keep in mind when you're developing Chairables. And I was wondering, they all sound like things that I can imagine not all designers pay attention to. So I wonder if you can identify one of them as like the largest reason for abandonment, or like does one of them particularly stand out in existing technologies?
That's a very good question. So with those 5, I think for abandonment, oftentimes it ends up being, I think if you had to choose one, it's probably tailoring, right? So it goes back to this idea of bespoke solutions. If the device is either not tailored or not tailorable, then it's really not going to, a person's not going to continue to use it if there's any issues. In terms of what the second most important one there would be that always available or always on. And I say that because it is also a little ambiguous as to what I mean by always available. You know, always available gives you a range of options. If it's always available because it's nearby and I can reach it, that counts as always available, but it doesn't necessarily need to be on at all times. When we think of like devices you might carry, your laptop in your backpack, does that make it always available? As long as your backpack is available and as long as you can reach it. But actually bringing those controls into a space where that person can literally always reach it, right?
Another student question is wondering about your thoughts on sort of the trajectory of brain-computer interfaces for this kind of group. Do you view that as a short-term solution, long-term solution? You think it's not going to solve the situation at all?
I think brain-computer interfaces are one component of potential solutions in this space. So I try to shy away from kind of the one solution will solve all the problems. In some cases, so a lot of brain-computer interfaces, depending on how they're implemented, they use different signals. Not everyone can produce those signals in the general population, and so you can't always rely on that as an advancement. They're also quite invasive, and so some of them are quite invasive. The really effective ones often involve actually implanting something on the surface of the brain, and then that enables you very precise control or precise access to those signals. The further away from the actual surface of the brain you get, those systems sometimes degrade. I think that there's a lot of potential for that, and if we can train, especially for people with very severe impairments, where it really is the only option for providing a range of actions and functions, I think it's perfectly viable. I think there's definitely long-term implications as we get better. I think it's definitely a viable solution, and we should always get better at understanding the intent of actions as well.
Patrick, I'm interested in your lab's relationship with your users. Do you have people that you can follow long-term to see the trajectory of their use of potential solutions and new areas for refinement, or is it more like the basketball tournament where you get a chance and then they go their own ways?
Yeah. So ideally, we have both. The pandemic has definitely slowed down our current existing relationships, but what our plan is actually to work. So for the athletic space, is to actually work and to keep relationships with teams so we can work with them over a long period of time. It's really hard to understand whether something's going to be useful from a couple of practices, and especially not from one tournament. So we do need to actually work with folks over time. We have a few teams that are interested in working with us. And so once we can work out all of the pandemic related details, hopefully we'll be able to do some long-term deployments of those kinds of technologies. We also are building up the relationships on kind of the more medical side. So thinking about the interactive technologies and health sensing, being able to actually work in a long-term way with those participants. I wouldn't say it's quite at the level of being able to follow them, for months or years at a time, but should be able to get beyond the tournament style data collection. I think those kinds of opportunities are much better for a large number of people at one time versus having to work individually with folks over a shorter period.
All right, I'm noting that we're at time, so I'm going to be that guy and say thank you so much to Patrick for joining us. We wish it could have been in person, but we're thrilled that we got to hear from you regardless. And I know a number of members of our community are meeting with you throughout today, so thank you for spending some time with us.